Hello, and welcome to Differential Equations. This is lecture 32, Fourier series. Last time, we talked about expanding a function as an infinite series involving cosines. This time, we're going to talk about how to do this using sines and cosines at the same time. So consider the eigenvalue problem. Where we're going to have minus y double prime equals lambda y. And our boundary conditions are going to be y of 0 equals y of 2L, y prime of 0 equals y prime of 2L. And we want to consider this on the interval 0 to L. So we have a second order boundary value problem. So we have two boundary conditions. But notice that this is not a Sturm-Liouville problem, because in the Sturm-Liouville problem, we impose some boundary conditions on the left endpoint and some boundary conditions on the right endpoint. Whereas here, our boundary condition is saying that you have the same behavior at the left endpoint as at the right endpoint, right? We're mixing together the two endpoints, which is something we haven't done in the previous cases. So this is not a Sturm-Liouville problem in the way we've been talking about. Okay, so nevertheless, it is behaved very much like a Sturm-Liouville problem, as we will see. The characteristic equation is r squared plus lambda equal to 0, and it has roots r equal to plus minus square root of minus lambda. So we have three cases. Case one, let's think about what happens when lambda is negative. Let's introduce mu squared, so lambda is equal to minus mu squared with mu positive, so that then we can write the solutions as a multiple of e to the mu x plus a multiple of e to the minus mu x. Okay, so let's put in the boundary conditions. So here we have y of 0 would be a plus b. We need this to be equal to y of 2L, which is equal to a e to the 2 mu L plus b e to the minus 2 mu L, right, from which we deduce that a e to the 2 mu L is equal to b. And y prime of 0 is equal to mu a plus b, which we want to be equal to y prime of 2L, which would be mu times a e to the mu 2 mu L minus b e to the minus 2 mu L, right, from which we deduce that a e to the 2 mu L is equal to minus b. And so together we see that a is equal to 0 and b is equal to 0. So not an eigenvalue. Second case, what if lambda is equal to 0? In this case, y of x would be just a plus bx. Our first condition, y of 0 would be a. We want that to be equal to y of 2L, which would be equal to a plus 2bl, right? And so from there, we deduce that b is equal to 0. Our second condition, y prime of 0 would be b, and we want that to be equal to y prime of 2l, which is also b. So b equal to 0 takes care of that. So lambda equal to 0 is an eigenvalue. And its eigenspace is just made up of the constant functions. Which brings us to the third case when lambda is negative, sorry, lambda is positive. So let's say lambda is equal to mu squared with mu positive. So then the solutions have the form a times cosine of mu x plus b times sine of mu x. Let's impose our boundary conditions. So y of 0, cosine of 0 is 1, sine of 0 is 0, so that's just a. We want that to be equal to y of 2l, which would be a cosine 2 mu l plus b sine 2 mu l. We also want the derivatives to match. So that's y prime of 0. That would be mu times b. And we need that to be equal to y prime of 2l, which would be mu times minus a sine of 2 mu l plus b cosine of 2 mu l. Okay, we want to solve this. Let's write it in matrix vector form. So the coefficients of A, I would have cosine 2 mu L minus 1 and minus sine of 2 mu L. Then here's sine of 2 mu L and cosine 2 mu L minus 1. It's multiplying AB equals 0, 0. Right, so this is what we get if we put these on the right-hand side. So we get an equation with 0. And we're going to get an eigenvalue whenever there are multiple solutions to this, right? Because if there's only one solution, that solution has to be the 0 vector. If I put a equal to 0 and b equal to 0, that certainly solves this system. So we're looking for when are there non-zero solutions, and that's exactly when the determinant of this matrix is 0. Right, and the determinant of this matrix is cosine 2 mu L minus 1 squared plus sine 2 mu L squared. Right, we want that to be equal to 0. Okay, so we have two real numbers squared adding up to 0. That means they each have to be equal to 0. So this will happen precisely when cosine of 2 mu L has to be 1 and sine of 2 mu L has to be 0. Okay, so cosine of 2 mu L equals 1. That means that 2 mu L has to be a multiple of 2 pi. And for those, sine is automatically 0. So we only need to satisfy this condition. And so that will happen when 2 mu L, because mu is positive, it will have to be a positive multiple of 2 pi. So we have 2 pi or 4 pi or 6 pi, etc. So that's the same as saying that mu is n times pi over L, such that n is equal to 1, 2, and so on. Okay, so those are the that mu squared is the eigenvalue. So the eigenvalue would be n mu over lambda squared. And the corresponding eigenspace would be A times cosine of n mu over L x plus B times sine of n pi over L x, such that A and B are arbitrary. Okay, so there are a couple of things to point out here. One of them is that, remember the Sturm-Liouville theorem, every eigenspace was just a multiple of a single function, right? In this case, we already noticed that we don't have a Sturm-Liouville problem. And indeed, the Sturm-Liouville theorem's conclusions already don't hold here, because we have this eigenspace and it's not just the multiples of one function, it's linear combinations of these two functions. Right? That's one thing to notice. The other thing to notice is that just like for the sine series and the cosine series, the arguments of these trigonometric functions are n pi over L x. Right? So that's the reason why we're considering this problem on the interval 0 to L instead of 0L, right? If we had done 0L, we would have ended up with a slightly different argument. It would say n times 2 pi divided by L in both of these, right? And so just because we like to have this look exactly the same as it did in the sine and cosine series, we chose to use the interval 0 to L. Okay. Very good. So now that we've found all of the eigenvalues and eigenfunctions, let's keep going. Right, so our list of eigenfunctions, the function 1, then we have cosine n pi over Lx, where n goes from 1 to infinity. And we have sine n pi over Lx, where n goes from 1 to infinity. And these are eigenfunctions on the interval 0 to L. We can't appeal to the Sturm-Liouville theorem to verify their orthogonality. But it's still true. And easy to check directly. Indeed, using the same trigonometric identities that we used before. So product of cosines is 1/2 cosine of the difference of the angles plus cosine of the sum of the angles. Right? Product of sines is 1/2 cosine of the difference minus cosine of the sum. And sine times cosine is 1/2 of sine of the difference plus sine of the sum. Using these identities, it's easy to check that if you multiply two of these eigenfunctions together, for example, if you multiply one times one, you get 2L. If you multiply 1 times sine, well, notice that you're integrating over a full period of sine, and the integral over a full period gives you 0. Same thing when you do cosine. And then if you multiply a sine eigenfunction against another sine eigenfunction, you get L if n is equal to m, and 0 if n is not equal to m. And when you multiply cosines together, you get L if n is equal to m, 0 if n is not equal to m. And when you multiply a cosine against a sine, you get 0. So these eigenfunctions that we obtained are indeed orthogonal on the interval 0 to L. Now, just as for Sturm-Liouville problems, from here we know that if you have a function which can be written as an infinite linear combination of these eigenfunctions, then A0 would be 1 over 2L times the integral from 0 to L of 1 times f of x dx, right? Where as usual, this 1 over 2L, it comes from dividing by the integral of 1 with 1. An would be 1 over L times the integral from 0 to 2L of f of x times cosine of n pi over Lx, right? Where this 1 over L comes from this L from the integral of cosine against cosine. And Bn would be 1 over L integral from 0 to 2L of f of x sine of n pi over Lx dx, where this 1 over L comes from this L, from integrating sine squared. We call this the Fourier series of f on the interval 0 to L. Okay, and so even though this is not a Sturm-Liouville problem, it turns out that we have the same convergence criterion as for a Sturm-Liouville problem. If f is any function defined on the interval 0 to L, and f prime are piecewise continuous, then the Fourier series of f converges at every point in the interior of the interval, and if you write down this series, which we've just said converges, then what it converges to is the average of the limits from the left and from the right of the function f at the particular point you're looking at. So if you're looking at a point where f is continuous, then the Fourier series converges to the value f of x. But if you're looking at a point where f is discontinuous, right? Well, because f is piecewise continuous, we know that it has a jump singularity. So we know that it has a limit from the left and a limit from the right. And this says that the Fourier series converges to the average of those two limits. Okay. So as an example, let's compute the Fourier series of the function f of x equals x on the interval 0 to L. Okay, so we need to compute these coefficients. So a0 would be 1 over 2L times the integral from 0 to 2L of x dx, 1 over 2L x squared over 2, evaluated at 0 and 2L, which is 2L squared divided by 4L, right, or just L. Then an be 1 over L times the integral from 0 to L, x times cosine n pi over L x dx. So we're going to integrate by parts as usual. We'll pick u to be x, so dv will be cosine n pi over L x dx. That makes du equal to dx and v equal to L over n pi times sine of n pi over Lx. Right. So this is 1 over L, and then we have u times v, so it's Lx divided by n pi sine of n pi over L x evaluated at 0 and 2L minus the integral from 0 to L of v du, so that's L over n pi sine of n pi over L x dx. Okay, so let's stare at this. Here, this integral, we're integrating sine over a full period, right? So this is periodic with period 2L divided by n. So we're getting n full periods, so that integrates to 0. This term, we're evaluating sine at sine of n pi over L at 2L and at 0. And both of those, sine is 0. So this altogether is just 0. And then Bn, the integral from 1 over L of integral over 0 to 2L x times sine n pi over L times x dx. We integrate by parts. U is equal to x, dv is sine n pi over Lx dx. So that makes du equal to dx, and v would be equal to minus L over n pi times cosine of n pi over L x. So that means we have 1 over L times u times v, so that would be minus Lx over n pi times cosine of n pi over Lx evaluated at 0 and 2L minus the integral of L over n pi of minus L over n pi cosine of n pi over L x dx. Okay, so let's stare at this. This integral, by the same reasoning as we used here, the fact that we're integrating cosine over, without the endpoints, 0 to 12, over n periods, n full periods, that just integrates to 0, right? So this, we're just going to have this first term, right? So that would be minus. So we're just going to have this first term, and we're going to evaluate at 2L and at 0. When we evaluate at 0, because of this x, we're just going to get 0. So it's just at the top endpoint. So we have 1 over L times minus 2L squared over n pi times cosine. Okay, and I'm going to put in x equal to 2L, so I end up with 2n times pi. Cosine of 2n pi is equal to 1. And so we just end up with minus 2L over n pi. So putting this together, we see that the Fourier series of x is equal to L plus the sum, n goes from 1 to infinity, of, well, we have minus 2L over n pi times the cosine, no, times sine. So let's put 0 times cosine n pi over Lx plus minus 2L over n pi times sine n pi over Lx. Right? So of course, there's no need to put that 0, right? This is just 0. So we end up with, here I'll pull out minus 2L over pi, and I'm just left with a sum, n goes from 1 to infinity, of 1 over n sine of n pi over L x. Right, and we know this converges for all x's in the interior of that interval. Okay, let's do another example. Let's compute the Fourier series of a discontinuous function. So let's say we take f of x is equal to x if 0 is less than or equal to x less than or equal to L, and then 0 if L is less than x less than or equal to 2L. Right? So we want the Fourier series of this on 2L, on the interval 0 to 2L. Okay, so let's compute the coefficients. We have a0 would be the integral from 1 over 2L, integral 0 to 2L of f of x dx. So since f is 0 from L to 2L, this is just the integral up to L of x dx. So it would be 1 over 2L times L squared over 2, and so L over 4. Right, next, an would be 1 over L times the integral from 0 to 2L of f of x cosine of n pi over L x. So again, since f is 0 on the second half of that interval, we can just write this integral from 0 to L of x times cosine n pi over Lx dx. Right, and so we would integrate by parts, but since we just did that here, we can just read off. We're going to have the same things occurring, but only going from 0 to L. So this would be 1 over L, and then I have L x over n pi sine n pi over L x, evaluated between 0 and pi, minus the integral from 0 to 2L, and not 2L, L over n pi sine of n pi over L x dx. Right, okay, so this is no longer automatically 0. This first term is automatically 0. So if you evaluate it at L, you get here sine of n pi, and that's always 0. And if you evaluate it 0, then this is 0, and so is this. So we get 0. But this term is not automatically 0. So what we get is 1 over L, and then we have minus L squared over n pi squared. And actually, when I integrate the sine, I get minus cosine, so that makes this a plus. I end up with cosine n pi over L x evaluated between 0 and L. So that gives us, okay, this constant out front, we have L over n pi squared. And then here we have cosine of n pi minus cosine of 0, which is 1. So that's L over n pi squared times minus 1 to the n minus 1. And so that's equal to 0 if n is even, and minus 2 L over n pi squared if n is odd. Okay, Bn is 1 over L, integral from 0 to 2L, f of x sine n pi over L x dx, which is 1 over L, integral from 0 to L of x sine n pi over L x dx. So we integrate by parts, but again, it's the same integration by parts we did up here, except that our endpoints are 0 and L instead of 0 and 2L. So we can just write down this 1 over L, and then here I have minus L x over n pi cosine n pi over L x evaluated at 0 and L, minus the integral from 0 to L of minus L over n pi cosine n pi over L x dx. Okay, and so that gives us 1 over L minus L squared over n pi cosine n pi plus 1 over n pi times the integral of this cosine, so that's L over n pi sine of n pi over L x evaluated between 0 and L. Right? So here, if you evaluate sine at either endpoint, you get 0. So we're just left with this term, right? And that's minus L over n pi times this cosine, which is minus 1 to the n. Okay, so we can conclude that the Fourier series of the function, which is equal to x if 0 is less than or equal to x less than or equal to L, and 0 if 0 is less than x less than or equal to 2L, on the interval 0 to L, is L over 4 plus the sum. K goes from 0 to infinity. So for the cosine terms, only the odd ones show up. So we're going to have minus 2L over, and instead of n, we're going to put 2K plus 1, because we only want the odd ones. Right, the cosine of, instead of n, I'm going to put 2K plus 1, pi over L x. Right, and then the sum, n goes from 1 to infinity. The sine terms, I have minus L over n pi times minus 1 to the n sine n pi over L x. Okay, and so we know that this series converges to x if 0 is less than x less than L, to 0 if L is less than x less than 2L, right? Because on this open interval and this open interval, our function is continuous. And it converges to the average of the limit as you approach L from the left, plus the limit as you approach L from the right, at x equal to L. So that's 1/2 of L plus 0, which is L over 2, if x is equal to L. Okay, let's do another discontinuous example. This one is known as the square wave. So let's compute the Fourier series of f of x given by 1 if x is between 0 and L, and 0 if x is between L and 2L on the interval 0 to L. Okay, so we compute the coefficients. A0 would be 1 over 2L times the integral from 0 to L of f of x dx. Right? So here that means the integral from 0 to L of function 1. So that integrates to L divided by 2L is just 1/2. An would be 1 over L, integral from 0 to 2L of f of x times cosine of n pi over Lx dx. So that would be 1 over L, the integral from 0 to L of 1 times cosine n pi over Lx dx. So that's 1 over L. And this is L over n pi sine of n pi over L x evaluated at 0 and L. Right? And as we've used a couple times now, if you evaluate sine n pi over L x at either L or 0, you get 0. So it's just 0. Bn would be 1 over L, integral from 0 to L, f of x sine n pi over Lx dx. So that's 1 over L, integral from 0 to L of 1 times sine of n pi over L x dx. So that would be 1 over L times minus L over n pi cosine of n pi over Lx evaluated at 0 and L. So that would be minus 1 over n pi. Cosine of n pi would be minus 1 to the n. Cosine of 0 is 1. And so altogether we have 0 if n is even, and 2 over n pi if n is odd. So the Fourier series of f is 1/2 plus the sum k goes from 0 to infinity of 2 over 2k plus 1 pi times sine of 2k plus 1 pi over L x. Okay, and for this series, we know that the series converges to 1 if x is in between 0 and L, and 0 if x is in between L and 2L, and at the midpoint, it converges to the average of the one-sided limits. So that's the limit as you approach L from the left, and the limit as you approach L from the right, which is just equal to 1/2 times 1 plus 0, so 1/2. X equal to L. Okay, so let's reflect a little on this. Note that the partial sums, right? So if instead of taking this infinite series, you were to stop after taking a few terms, you get a continuous function. Their graphs look something like, okay, so let's say that here's L and here's 2L, and here is the function we started with. Then let's see, I know it's equal to 1/2 here and it's 1/2 here. And what it'll do is go up something like that. And then if I include more terms, it might look something like that. And if you include even more terms, then it might look something like that. So what's remarkable is that it turns out that no matter how many terms we include, in the partial sum, there will always be an overshoot right before the singularity. And this overshoot is always about 9% of the size of the jump. Right? This is known as the Gibbs phenomenon. Right? So see over here, as you take more and more terms, the oscillations get smaller and smaller because you are, of course, converging to this function, right? As you include more terms, this overshoot moves further and further to the left here or to the right here. It's approaching the singularity, right? But what's remarkable is that the size of the jump, how far you go over, doesn't change. You're always going up by about 9% of the jump. It doesn't contradict the pointwise convergence of the Fourier series, because the overshoot moves closer and closer to the discontinuity as we include more terms. Right? So we still have the pointwise convergence that we've asserted before. What's happening is that the convergence is not uniform, right? And that's the way it has to be, because our limit is not a continuous function. So there's no way you could have uniform convergence of continuous functions to it. This phenomenon is important. It shows up in applications in the real world. It has a name. In signal processing, it causes what are called ringing artifacts. Here, the word artifact is used in the sense of something artificial, so something that's added, not there in the original signal. So here we have spurious signals that appear near sharp transitions. Visually, they appear as bands, or they're called ghosts. Near edges. They typically appear as multiple fine parallel lines. Immediately adjacent to high contrast interfaces. it can be problematic for things like spinal imaging, in which they may make the spinal cord appear wider or narrower than it really is. It's known as the Gibbs phenomenon after Josiah Willard Gibbs, who lived from 1839 to 1903. He was an important American physicist who obtained the first American doctorate in engineering, Yale, class of 1863. Okay, we'll stop there and pick it up from there next time.